Thank you all for joining. So I think in the interest of time, we can start, and hopefully the rest will join us along the way. So what I actually plan to do, I plan to start by looking at what we covered last week. Then we can look at the quiz as well. And there was a question I had posted on R for Fun Club. I think today is an opportune time to do it as well and finalize on it. So I'll just quickly share my screen. So let me see. Okay. So this was the work that we did last week. And for this work, what we were doing, we looked at how we can combine plots in R, and with the sole goal of trying to actually do something like a comparative study when you have different visualizations. And you see that the plots that you'll be combining is not necessarily they have to be of the same geometry. It can be just different plots that you're actually doing this. So we looked at the packages which are used in combining plots. We saw there was Cowplot, GridExtra, and Patchwork. And these ones are actually supposed to be installed before you actually load them into your source code. Then we also looked at examples where we actually used Patchwork, and we saw that after you actually load the library, that is Patchwork, what you need to do to your clean data, you just need to actually have a way that you want these plots to be. But remember, you also needed to have assigned names to those specific plots because they're the ones which you'll be calling when you want to actually combine them. Then we also looked at GridExtra. GridExtra, this one, once you have loaded your the package that is the GridExtra, the syntax for actually combining the plots was that you use grid.arrange, then you actually list the plots that you want to be there, and the order of how you list them will actually determine how they will be. Will also determine the order as to how the combined plot will also look like. But this one actually has an extra option whereby you are also able to define the number of columns whereby these plots will be we will actually be slotted in. Then we also looked at Cowplot. Cowplot also, the package had to be loaded, that is library Cowplot. And the syntax for using this was you had to call up the function which is called a plot grid. And the plot grid then you defined the plots which you wanted to be combined. And also we also so that it is also possible to have different sizes of the plots within that combined plot, and that can be achieved by the option rel widths. Okay, so that's also what we saw, and also for combined plots, you also had an option of also defining the number of rows that you want those plots to appear, and also the labels as well. So this was as far as the combining of plots was concerned. We looked at the three, and we saw examples of each. Then after that, we also looked at a different type of visualization, which is called a Sankey plot. Next week, we'll start looking at alluvial, but next week we'll start looking at alluvial, but last week we covered the Sankey plots in R, and we saw that this is just supposed to show you how quantities are transferred from one set of categories to the other. So we saw that Sankey plots are also interactive, but we saw that they're web-based because they run on JavaScript, and they're useful when you actually want to emphasize on relationships and proportions and the flows of given data set. Then we had this example of wages versus the budget and how the expenses are actually gotten from that budget. And we saw that the flow, or what you're calling the link between the nodes. So in this case, you can see the wages, the ones which are in dark gray, those are what we call the nodes. The budget is a node. The taxes, housing, food, transport, all those are nodes. But what is linking these nodes are what we call the links. And we saw that the width of these links are actually proportional to the flow magnitude. So in this case, in this example that we're seeing right now, it means that taxes and housing and food actually take the largest portion of the budget. Okay, this is just a quick way to actually derive some of these proportions from different categories to the other. Then, so we saw that this was actually an example of a Sankey plot, and we saw that the key components for a Sankey plot are what we call the nodes. We also have the links or flows. Then we had the width of the links, but these ones are actually determined by the quantity or the magnitude of these values. Then we also had colors, and colors, these ones can be user defined. And as in the example that we saw last time, is that when we were trying to plot all the hospitals, we could see that all of them are actually taking the color black. So it's kind of we had exhausted the options that exist in the color palette for that particular Sankey plot. But it's possible to actually have user-defined color scales that we can see later that can be used in Sankey plot. So it doesn't mean that if you have as many nodes as possible, you can still have colors defined for these nodes as well. So we saw that how this actually works is that you need to identify the sources and the targets. And the key thing in this case was to make sure that the index or the indices were starting from zero. That was key. Then we also needed to define the flows. Details can be added, things like colors, labels, and all this can always be added to your Sankey plot for it to actually have a comprehensive meaning. Then there are so many packages that I've actually come to realize there's so many packages which are used to actually plot Sankey and alluvial diagrams. But the one which is commonly used is Network D3, which is an interactive Sankey diagram that uses JavaScript. And we also have now, there's one which is based on the ggplot framework, which is called the GG alluvial. We'll see this next week during our session. So there's the GG alluvial, which is based on the ggplot2 framework, and it's also used to plot alluvial diagrams. Then we also have river plot, which is also good for static Sankey diagrams. If you want actually to export those plots as PNG or JPEG, you can always opt to use the river plot. Then we also have Plotly. Plotly also allows Sankey diagrams with interactive features, just the same way as Network D3. So these are just part of examples of packages that can be used to draw or to actually visualize using Sankey and alluvial diagrams. And you'll also find that just within the ggplot2, we have a number of packages that are under ggplot2 that are used to draw Sankey and alluvial diagrams. I'll list them next week, but the one which we'll primarily use next week will be the GG alluvial. So I actually thought it would be wise we look at just a simple example of how a Sankey diagram can be done. So, and we say that remember the key components was that we needed to have our nodes. We actually need to have the links and the values between these links, that's what will actually determine the width of the links between these nodes. Okay. So let me. I have two examples here, which is actually in the notes that have been shared on the platform already. But I wanted us to look at this just two examples, just brief examples. We can look at them together. Then we look at how they actually look like. Okay. So let me open my. Let me share my R environment, unless there is any question so far before we proceed to the example. And for the materials that we used last week, everything was shared, so you can always go back and confirm what we did, and also try to practice more using the examples which are there. So let's see. I would like us first of all to do this before we go to the quiz, which is sent. So this one, you can see that for you to do this, first of all, you need to load the network D3, the one we saw last time. That was the package that we can use to draw alluvial and Sankey diagrams. Then remember, we also needed to have the nodes whereby now we can have links moving in between these nodes. Then as far as for the links is concerned, we need to know what is the source. Where are you moving from? Where are you moving to? And what is the value between these two? Okay. Then how to build this plot was just you call the Sankey network, which is a function within the network D3. Then you need to define the links. Okay. Let me since we're just here, let's look at a Sankey network. Let us look for more information on this. So you can see here, what you actually have is for you to draw this one, you can see the description is that it's a JavaScript Sankey diagram. Then you can see that you need to define the links, you need to define the nodes, you need to define the source, you need to define the target. At least these ones have to be there. You also need to define the value and the node ID. For the node ID, if you like labels on the nodes, you need to define also the node ID. Then, as I was saying, for the color scale, this one can be changed. It can be user defined, and you have to do this within the JavaScript D3 framework. Okay, because it also has its own the way those colors have been defined. Then you can also do things like the font size, font family. These ones can be defined. But another element we will look at is what is called the last option here, which is called the sync right, which equals to true. In the last session, we did not have this option, but it's also a good option that we can actually look at here in this example. So you can see, for that matter, so from our two data sets, the one which defines the node and the one which defines the links, we can see that for the nodes, we have the nodes. Our nodes will be A, B, C, D, and E. Okay, just as simple as that. We just give the nodes those names. Then we also want to have the source and the targets moving from 0 to 2, 0 to 3, 1 to 3, 1 to 4, 2 to 4. We'll actually look at this and actually change a bit of it and to see how it changes. But then the value is an important element because this one actually gives the width of the arrows or the links between these two, between these nodes. Okay, so since we have everything, but I would like, first of all, because by default sync rate is false, but in shortly, sorry, by default is always true, but we can use false first, then we see how this one looks like. So if we actually run this, so our nodes, and you'll see these are just two data frames which have been created. So if we check at how the nodes look like, you can see it's just a node with the labels A, B, C, and D. How about the links? So the links will also be another data frame. Oh, sorry, I've not run the whole thing first. So the links will be, so you can just run this. So you can see it's the source, target, and the value. So we now need to connect the links and our nodes. So remember now that the source and the target, what you actually need to look at is that the values in the nodes, like A, will be at position 0 because it's the source, the index starts from 0. So this one will be 0, B will be 1, C will be 2, D will be 3, E will be 4. So when I come to the source and the target, it means that this first element, which is 0, it means that I am moving from A, from the node A, but the target will be 2. So 2 means it will be node C. And the value between these two, that is A and C, will be 10. Okay? So you can actually think of something like two hospitals, hospital A, hospital C. How many patients are moving from hospital A to hospital C? That can be the value 10. Okay? Then if you look at the second element, it means that I am still moving from node A, but the target in this case is D, because this is 0, 1, 2, 3. So 3 means I'm moving to node D, but the value will just be 5, the flow values, which will actually determine the width of the arrows between these two nodes. The highest being 15, and 15 is because I will be moving from source, which is 1 in this case is B, and I'm moving to 3. 3 in this case is 0, 1, 2, 3, D. Okay, that's just how this source and target and value and the nodes actually come into play when you are dealing with a Sankey diagram. So let's see. So in this case, of course, the links will have to define by the links which have been defined here, where we have the source and the target. Then you have the nodes. The nodes are defined by line 4, which is the data frame that contains the nodes where, or rather the categories where we want to establish that movement from each other. Then you can have the source. Yeah, the source we can define it is the source, which is a column in the links data frame. Then we can have the target. The target is also a target, the name of that column. Then you can have values. Then since we want names to actually appear on these nodes, you can have what is called the node ID. And the node ID basically will just be the name, and the name will be how we have actually named the nodes in data frame in row number 4. Okay. Then we can have a sync write. Sync write we'll see what actually happens from this. Okay. So this is just a simple Sankey plot that we can just use so that we can actually have ideas when it comes to complex Sankey plots, how they actually behave. Then, so if we run this, let's see, you can see what has actually appeared, and we can actually look at this together. You can see that if you look at the first element in the source, that is a 0, that is line 8, 0 is moving up to 2, and 2 we have said is C, is the node C in line number 4. So, and you can see there's that width which is moving from A up to C. That's correct. Then the second one is also moving from 0, which is A, up to 3, and we've said 3 is D. So you can see A is moving from 0 up to D, that is the other link. But then also in the source, we have, that is the third element, that is 1. 1 means it's coming from B and is going up to 3. So we can have B to D, that's correct, the one which is actually becoming active here. Then we can also move from 1 up to 4, and in this case, we can also move from 1 up to 4, and in this case, you can actually see it's 1 to 4. So 1, 4, and 1, this means that we're moving from B up to D. That is that one. B up to D. This 1 to 4 is actually 1 up to E, because E is our fourth element in the nodes. Okay. But then let's see at the last one here. The last one here is from in the source is moving from 2, and we know 2 is node C, and it's moving to 4, which is E. So you can see that, so it is this one here, from C up to E. And you can see, since we have the node ID equals to name, you can see our nodes have actually been named. And the good thing is that if we just place the cursor on one of these flows, it actually shows you where it is flowing to and from. Like this one, you can see I've just placed the cursor in the one which is active now. The flow from A up to C. So you can see it has actually highlighted. It has actually given me the information about that flow. It is saying that is it from A to C, and the value is 10. Okay. Now, let's see. Sankey, please check. Sankey, right? In this case, is false. Let us change it to true, and we see how this will look like. So if it's true, what has actually happened? You can see that A, D, and E have actually moved towards the end, okay, in this diagram. So what has actually happened, if we go to the help and we read at the description of the Sankey, right, or of the sinks, right, that option, it's a Boolean, so it is either true or false. So it means that if it's true, the last nodes are moved to the right border of the plot. And it's true because our from what we're actually plotting, it means that our last nodes, for example, our last node on the left is actually A. So A has been moved to the edge of the plot, and our last nodes on the end is actually D and E. So they've actually been moved to the end of that plot on our right, so that at least this one makes the plot to be a bit tidy, so that you can actually get to see the flow clearly. Okay, so you can see that for A actually there's an option of A up to B, then B to D. Okay, then this one is A to C, C to E. There is B to E, B to D. Yes, and it's 15 because B is 1 and it's moving up to 4. That is the fourth element in the source. And E to C. So this one, if you look at this one, A to D, it has highlighted a flow that is moving directly up to D. So it is from A up to D, and the value is 5. Okay. So this is just one way that you can add options to our Sankey network. At least this one is a simple example that explains why we need to define the nodes, why we need to define the source, why we need to define the target and the values. Okay, because those are the most important options that need to be in that Sankey network function. Okay. Then in that same example, we also had another one which was a bit interactive because it had, now it is it had, let us copy this as well. So in this case now, let me copy up to there. This one now, what is actually happening? This one now, what we have, let me cross this one so that it doesn't cause confusion. So please take note of the sync rate as an option to actually make the visualization to be a bit less messy. Where do we use such visualization? Such visualizations are actually used, for example, when you want to visualize the flow of values between two different categories. Like Frank, just hold on to that thought. We look at this example here where we have just some random data from the hospital, where you have there's some patients who have been admitted, those who are emergency, just those ones who are coming for a routine checkup. We have those who are HIV positive, HIV negative, those who are on ART, those who are not on ART, those who have recovered, those with complications and deceased and alive, all this. Now, what this one just tries to show or to visualize, it just tries to show you, or rather to actually quantify the progress or the cascade of things like population or values from different categories to one another, from one category to another. Okay, and for this example, it can be of those who have been admitted, how many go to emergency, how many proceed to how many were actually from the routine checkup, how many were diagnosed with HIV, how many were not, how many were placed on the ART, how many are not on ART, how many recovered, how many ended up with complications, how many died, or how many are alive. Okay, so this is just a way to actually just to visualize the cascade, or rather the flow of values between different categories. Is that okay, Frank?
Yes.
Okay. So let's okay, no problem. So let's look at this just short example here again, but now this one, instead of having dummy nodes, we can have actually categories from the hospital, and you just would like to show just a quick visualization of how people are actually moving from one station to one another. That can actually be done by this. So in this one, because we want to use the Sankey, in the Sankey network, we want to use the sync equals to true. Let's see. So you can see this one from this visualization here, it actually shows that those people who are among those who are people who went to the hospital, a huge proportion was actually admitted. Okay, and then some proceeded to emergency, and from those who proceeded to emergency, it seems like a bigger portion was actually found to be HIV positive, just from this 40, and those who were found to be HIV negative from the emergency were actually just 10. Okay, from the routine checkup, it was found that those who were actually found to be HIV positive were 15, and those who were not was just about 15 again, so it's half and half. Then, from those who are HIV positive, we can see that a bigger proportion was actually placed under antiretroviral therapy, while of those still who are found to be HIV positive, about 15 of them did not proceed to be recruited under ART. Okay, then we can look at among those who are under HIV, who are HIV negative. Definitely a bigger portion did not need ART, but maybe a number of them were actually placed under some preventive measures for HIV, just to continue suppressing the viral load. Then you can see that among those who are under ART, a huge percentage of them ended up recovering, or rather, virally suppressed in this case. Those who were actually found HIV positive but proceeded to not under ART, some of them may have developed complications as part of that. And then you're actually able to see now the proportion of those who ended up being dead and others who are alive. Now, the beauty of this, as we'll see next week, we can now actually add the actual percentages. Instead of just having admitted, emergency, routine, HIV, and etc., we will also now annotate these values so that in as much as this flow is becoming active when I move the cursor here, you'll also be able to see the actual percentages of those people who are moving through different categories. And I think that with that addition now, it even makes it more powerful when you want to do a presentation of given categories who are cascading those different sections in a hospital. That can be a useful visualization for you. Okay, so the same thing that we're doing for the other example, where we just looked at the movement between different nodes. That's the same thing that we're doing here, but in this case, you'll see that the number of nodes are, I think they're about 8 in this case. Okay, so the 8, you'll have at least 8 sources, but it's not a must because some nodes, it's not a must that they have links. Okay, then values, as we said, this one will actually determine the proportion or the size of that link. Just for argument's sake, like in this case, in our example here, where we have value, let me, instead of 50, the first flow that is moving from admitted to emergency, let us change it to something like just 200, just for argument's sake. We see how that plot will look like. So I expect that the link from admitted to emergency, that proportion to actually increase again. And you can see just by changing the value from admitted to emergency, I've increased it to 200 from 50. You can see that now this proportion is actually even bigger now. Okay, but now we'll see, and the reason why now some of them are becoming smaller is because 200 is much larger as compared to some of the values that we have, like 10. It is 20 times bigger than 10. So we expect that some of these flows to be 20 times less than that. Sorry, at least 10 times less than that. Okay. So that's basically just a simple Sankey network that one can use, as long as you have the source, or you have the nodes, and you know the cascade between these different categories. You can always use a Sankey network for that visualization. Okay. So just for let's try and instead of these things right, let's just have it as false, and we see how this plot will look like. How will this plot look like now? Because with the things right equals to false, it means that now it's not a must that the end nodes be towards the end of the plots. So you can see, so it's not a must that they now move to the end of the plots. So that is an option that you can always consider when you're doing a Sankey network. You can always consider using that option of things right. Ah, wonderful. I can see Ashna shared. Ashna, could you kindly open for us? We see that Sankey diagram.
Yes, I can just show my screen. It was a very similar one to the one that you were sharing, just to illustrate that, Sankey diagrams
yeah.
are quite popular in patient care pathways in general. So this is a very similar. This one's on COVID instead of
Okay.
HIV, but very similarly kind of shows patient care pathways.
Oh, wonderful, wonderful.
Yeah, I just wanted to share that sort of other application.
Yeah, thank you. Thank you. Thank you so much. I think that one, even for a person who would just like to have a quick idea on the numbers that were going through the hospital, those who are being hospitalized, those who are at home-based care, I think that Sankey diagram gave that information very well. Okay, thank you, Ashna. So I don't know, do we have any other question before we look at something else before we call it a day? There's something which I had shared. I'll just show you quickly what we had shared on the there was this sorry, let me open. I'll try to be as quick as possible. So there's only one thing which we have been postponing to do, but I would like us to do it today. I'd like us to do it today, then we'll see. Azumani, you're asking how do you add color? Yes, how do you add color? I will just come to that shortly. Let me share my screen. Do you remember this example that we that I had shared on the Art for Fun Club that was in a bit to understand the relationship between ice cream sales and UFO identification or sightings? A code was used to develop that visualization. So the task was actually trying to fill the missing parts just by looking at how the flow, the diagram looked like. You're just supposed to come up with an idea of the missing parts. So I would like us to do this today. Then I will also upload the code which I used, but there's just a small element I would like us to discuss together, first of all. So there was something Athmani had asked that is about how do we add color. If you look at help for the Sankey network, there's this part which is called there's this option which is called the color scale. It goes to JS. You can you can copy that there. Then you can come and place it as an option in your Sankey network. Then now for this one, you just check in the JavaScript site, D3 site, how they're actually naming this color. So you may find that you may need only to replace this one, this part here, and it becomes a different plot. So like, for example, like I think there is a scheme category 10. Let's check how scheme category 10 will look like. If I change this to 10, let's see how the plot will look like. But these color scales are defined. Yeah, you can see it has changed so that a live becomes magenta, emergency become orange. Okay. So that's how you actually change the color scales of a Sankey diagram. There's this link here which has been given here. There are so many types of these color scales. So you just have to choose the one which actually works for your visualization. So that link is given here. You can see here this color scale, character string specifying the category color scale for the nodes. See this one. So if you go to this link, you can see those color scales. And those ones you just need to copy the actual name which is given there, the one that you want. Is that okay, Atumani?
Yes, thank you. Thank you very much.
Okay, wonderful. Thank you. So now, allow me to digress a little bit to show you something. So I know in the first training, there was a day Frank showed us how we randomly generate numbers. So in this case, there's this, we can generate numbers like, let me first show you. Let me say, set C to be like something like 5. Then I want something like D1 to be R norm, randomly generated, normally distributed values. Let me say I want 4 values, okay? Then D2, I want also to generate randomly distributed values, also 4, okay? But now, let's see, are these values similar? Is D1 and D2 similar? So there's a function in R which is called identical. Let's see if D1 and D2 are identical. So we just need to know, is D1 and D2 identical? They're randomly distributed, but we would like to know, are they? So you can see false here, okay? You can see it's false in the, okay, let me just do this a bit so that you can see. So let me run this again. I'm just trying to randomly generate some values. So you can see in this case, identical D1, D2 is saying it is false, okay? But now there's an option of doing 1, 2, 3. It's an option in R where you're just randomly generating values that will ensure there's reproducibility, ensuring reproducibility, like that. So if I do this, and for the same 4 values that you're randomly generating, let's see whether these two are identical. Oh, still false. Let's see. It's still false. Let me increase this to like 10 values. And you see, because the seed now is much larger. And you see whether these two will be identical. Still false. Let me increase this to 100. The power of large numbers, and we see. Oh, still false. It's still giving me false, but this one is, I'm just setting the seed to be 1, 2, 3, so that in the example of the UFO, I was just trying to randomly just create a data set that can be used in this case. Then the other thing I would just like to we talk about is something to do with dates. So suppose today I say today as date, I'm just this concept. I know Ashna will cover it in our next session, but there's something I want to do that will enable you to understand that example. So I have this one as date, and I know if I want to print date, you can see that one, it has given me date. But now, what has actually happened here, it means that the format here is, you can have %D, %B, and %year. So this one will be for year, this one will be for month, and this one will be for the date, okay? So what I want to do, I just would like to extract, I would like to format that today. What I want to extract, I just want to extract the month. if the date in your data is given as this, I just want to extract the month. So let me see whether this will actually work. Control C. Then it's Jan. So you can see, if I do this in my data set which has dates, then I'll be able to extract the month. That's all I wanted to digress. I know Ashna will cover a lot of this in the time series part, but what I wanted to show was just the answer to the quiz which was given on the platform. So don't worry about the seed, because the seed, as I said, is just supposed to generate for you random numbers that will ensure that there's reproducibility. If you do different runs, they're supposed to be identical as much as possible. Then my UFO data, the one I was creating, I was just saying that I want the dates to move from January 2024 to actually the end of December, okay? And the temperature, I just wanted it to be randomly distributed for the 365 days. So with this, I'll ensure that the number of times I run the values of temperature, because it's randomly distributed, randomly generated, they will be as identical as possible between different iterations. Then with a mean of 7 throughout the year and a standard deviation of 7, okay? And I want it to be rounded to at least 1 decimal place. Then the same thing with the ice cream sales, but for UFO sightings, because this one has to be discrete, we use the Poisson distribution. So this one was just a way of generating that UFO data. It's just a synthetic data that that we use for that example. Then this was the formatting I was talking about. I just wanted to extract the month in my dataset UFO data. I just wanted to extract the month, and there are some days within the year I wanted that to be given not a value. So I can just use sample. So the reason why we are doing the seeding in line 4 was to ensure that we are able to reproduce randomly distributed Poisson distribution of those values, and we can also be able to use the sample here. Okay, it's just a way of just putting some missing values in that data. Okay, then since the month column has been created, now we can actually build on what Ludovic covered about mutation, and also what Ashna had covered previously, that is for the case when. We just say that there are some months, we want them to be considered as winter months, some to be considered as spring, some to be considered as summer, okay? This one is a logical expression that tries to show the month, if it's December, January, and February, that want to be considered that as winter and etc. Okay. The quiz was actually in this part where you're supposed to fill what was actually missing. So you can see that like for the first element, what was missing was the color. Color was sightings. Okay. Then the titles and the facet trap, what was missing was the word season, because you could see the facet traps were depending on the seasons. So that was what was missing in that plot. Then what else? So you can see that for the facet plots, those subplots, we could change the strip. The strip background is where the title of those subplots are. And in this case, they were the seasons, and we could use what is called a strip background. This option in the theme, the one we showed last, you remember the one we had so many options for adding user-controlled options for a plot. In this case, the strip background, which actually enables you to actually format the colors of those in a facet trap or facet grid. So some of those items which were missing was this part here. All of them are now listed here. Let's see at how the plot will look like. And for the geom smooth, I know we can use LOS here, line number 34, or just the linear model. You can check on geom smooth how many options are there. There's LOS, there's LM, there's GLM, there's GAM, so many. But in this case, let us just use a linear model that will feed that data to that. So this is just to play around, but I will also send this code so that you can just look at it and try to internalize what was actually happening. Okay. So you can see that was the answer to that challenge, which was posted on the R for Fun Club. So what was actually missing? What were the labels which were missing? How was the plot created? So this one is we said it was a facet plot, facet trap. That is. So let's just put two columns in this case, and we see how it looks like. Yeah, so that's it. So otherwise, I think that's the answer to the challenge. I'll post this code as a reply to that example which was given at the R for Fun Club. You can check it out and just play around with it. Just try to change some values and see what you actually get. Okay. So otherwise, I would like to stop there for today. Unless there's any question. Okay. Thank you so much for joining. Ashna, do you have anything you would like to add?
Nothing from my end. As I said last time, I'm learning a lot in these sessions as well as someone who hasn't had much experience with Sankey plots and these types of visualizations before. So, thank you for your great presentations and examples.
Thank you. Thank you so much, Ashna. Then I think guys, all this will be posted on our platform. You can check it out. If you have any questions, you can ask us. You can ask Ashna, Frank, or Chioma, and we'll get back to you. Otherwise, I believe the only way that you can get to actually get the nitty-gritty of this is just by practicing, and just change those values and see what actually happens to the plots. I think that can also be a great way to learn how those options in the plottings actually work. So otherwise, thank you so much for joining us today. So we'll meet next week for the other part. So next week we'll do alluvial diagrams, and we'll see how alluvial diagrams actually differ from Sankey diagrams. Okay. Thank you so much, and see you next week.